Today I'm going to explain about the basic transformer in text analytics. This is the agenda. We are going to learn about what is sec to sec or sequence to sequence, and we are going to learn what the encoder and decoder, and we are going to learn about attention, what is attention in the NLP, and basic transformer. So this will include also some code, and we are going to do the code analysis. So let me review a little bit about the previous lecture. On the previous lecture, we learned about RNN. So in the RNN, we learn about several variants. For example, we have one-to-one, one-to-many, many-to-one, many-to-many with this structure, and we can also have many-to-many with this structure. However, when we have the RNN, actually RNN is limited in the ability to capture the long-term dependency. So if this one is too long, so it means if the word or the sentence is too long, or the paragraph is too long, so there might be some weaknesses. And also if we are doing the parallel computations, so it is also limited with RNN. So therefore, the idea of sequence to sequence, or usually people mention sec to sec, sequence to sequence, there are some use case application. For example, we can do the machine translation. So in the machine translation, it means that we can translate the text from one language to another. So for example, this is maybe from French to English. So we can create the sequence model and we can do the translation. We can also do the text summarization. Text summarization we learned previously. We use only the simple machine learning. We use the basic probabilistic to create a concise summary of a longer text. So when we have a very long text, we can apply the sequence model and we can create the summary. So that's text summarization. Chatbots and conversational engines. It means we can generate responses in a dialogue system. So if I have question, how are you doing today? So the chatbot will give you an answer. I'm doing well. Thank you. How are you doing today? So this is a kind of question and answer. Speech recognition. It means we want to get the spoken language. We want to convert the spoken language into text. Or another application would be about image captioning. In the image captioning, we are going to generate a descriptive text for a given image. So we give the image and then we can generate the text. So there are some application for using the sec to sec or sequence to sequence. And one of the basic things for this sequence to sequence is the encoder decoder. So we learn about encoder by the deep learning. Last week we learned about the RNN and we learned one concept about the encoder. So for example, if I have a word or if I have a sentence, she is eating a green apple. So in the machine translation, we are going to make the sentence tokenize into words. And then after we know the word, we are creating a factor. After we have a factor, then we make a context factor. So the context factor, it means that we are going to do something. Let's say if we are doing machine translation, then the factor or the context factor will be about what are the language that you want to convert. For example, if this is English, then I will have the context about English, and I want to know what is the target. So the target is Chinese, and it means the context will be English to Chinese. So after we apply this context factor, we can translate the English word into the Chinese language. And the Chinese language will be generated through the decoder. So that's why we usually call it as the encoder decoder. So this is the one of the step in the sequence to sequence. So the standard encoder decoder structure, which is based on the RNN, as you may know, we start with the H, or this is the hidden weight, hidden layer, and then it will be updated based on some model. For example, we can use RNN, or we can use LSTM, or we can use GRU, and then we can get the update of H1. We can get the update again H2. We can get the update H3 and so on. So this is based on the RNN. After we have the encoder from the RNN, we are going to check the semantic encoding context C. So this is what I mentioned before. If we want to do the machine translation, it is from English, for example, to Korean, then this is the context from English to Korean. If we want to do the speech recognition, then the first encoder will be the signal from the speech, and then we make the encoding from speech to text, S to T. Then we will do the decoder. So the decoder means we will generate the text, and we will have, this is SOS. SOS means start of sentence. So if you learn the sentence in the language model, we can have a model, and the model will have the starting of the sentence. So SOS, it indicates starting of the sentence. And yeah, we will go to every possible text. So we will generate every possible text, and then this text will go on the next as the input, and then we will predict what will be the best next word. And then after we know what is the possible next word, then it will be the input, and we will predict again what will be the best next one. And then it will be the input until we finish, until we get the EOS. So what is EOS? It is end of sentence, EOS. So this will be repeated until the end of the sentence. So there will be a function. So we already learned last week about the RNN. Whenever we have the it's, we have it's. So H1 will be the updated of hidden from the H0 with X1. This one. How about H2? H2 will be a function from the H1 combined with the X2 and so on. So it will be consecutively updated until the end. And then after we know the context, we will do the decoder. So the decoder, usually it is a text generation. So we learn also from the code that we have last time. Then the encoder. What is encoder? So the encoder processes the input sequence and compress its information to a fixed size context vector. If you still remember the code that we used last time, we have the input sequence. So from the word, from the sentences, we create the word or the token, and then we create the input sequence. After we have the input sequence, we want to compress the information into a fixed size context vector. So this vector acts as a summary of the input sequence and capture the essential information needed to generate the output sequence. So we have input, and we will use this input to do something in the maybe RNN or maybe LSTM or maybe GRU to generate the output. So the encoder is typically an RNN, LSTM, GRU that reads the input tokens one by one and updates its hidden state accordingly. Okay. So in the simple encoder, we can just pick the keyword. For example, I have the word I am happy. I am happy. So yeah, we can just simply fit this word into the box. It is maybe RNN or LSTM or GRU, and then we will get the updated H1, and then we will go to another RNN. We will go to another RNN until the end of the sentence. So the context factor means we are doing some thing after we read all the input. So if we finish with all the input, then we will do the context factor. So this factor contains the compressed information from the input sequence and serves as the initial input for the decoder. So this will be something to initiate the decoder. Therefore, this will plays a very important role. As I mentioned to you, if it is about English to Chinese, okay, then it will be a matrix that indicates how the English sentence can be translated to Chinese language. If we want to translate from English to Korean, then the semantic encoding context, it will be from English to Korean, okay, and so on. And the last, we have the decoder. So in the decoder, we will have another network, maybe RNN or LSTM or GRU, which can be in different network. And it takes the context vector from the encoder as its initial hidden state. Unlike the encoder, the decoder is designed to generate output tokens sequentially and one at a time. And its output token depends on the previous tokens generated by the decoder, as well as the current hidden state. So if you look at the figure, as I mentioned to you, this is the output from the start of the sentence. After we have the word y1, the y1 will be the input, and the y1 will be the input to update this hidden state, and this hidden state will determine the output. And after we have an output, this output will be the input for the next stage. And then again, we will train into a network, maybe RNN and so on. And then we will send an output, and the output will be the input for the next stage and so on. So the encoder, as you may know, the encoder processes the input sequence, for example, I am happy, and converts it into a context or encoded representation that capture its meaning. So let's say, yeah, I have what I am happy, then I will be sent to this hidden state with the network RNN, and then we will create a factor embedding. So after we have the RNN, there will be a factor. But sometimes people also give another embedding. If you still remember, when we learned about the language, the text representation. In the text representation, we can have the text representation such as the back of word. You still remember? The back of word, we want to check whether the word exists or not exists. We can use binary 0, 1. So if I am happy, then I can make a kind of table like this one. I am happy, and then we can have 1, 1, 1. So it means the word I is available, the word am is available, and the word happy is available. So we can use this kind of text representation. This is the traditional text representation. And at the time I also explained, we can use some advanced text representation. For example, we can use word to fact. At the time we learned about glove. We learn about fast text. We learn about the continuous back of word. So yeah, those things are some variants for the embedding. We can use this embedding here before we enter the RNN. So that's also the variation before we do the encoder. So each word passed through the encoder RNN or GRU or LSTM. Yeah, it updates the hidden state to integrate information from the entire sequence. So if we have this embedding, usually it will be more, the representation is more obvious. The representation for the word will be more objective. And at the end, the encoder outputs a final hidden states, and we call it, this is as the context factor, which is a condensed representation of the whole sentence, I am happy. So at the end, there will be a kind of representation for this word, I am happy. And let's say we are going to translate the word I am happy to Korean. Then the decoder takes this context factor and generate the output sequence one word at a time and translating it into the target language. For example, the target language is Korean. Then there is a possible translation, 나는 행복해. So the first, after we have the encoding context C from the encoder, it will run into a network. Let's say this is using RNN. We can also use different network, LSTM or GRU. And then the starting of the sentence will be fed into the RNN, and we will send the output. So there is a softmax to normalize or to make the numbers become more important to a certain text. So let's say we know the word I can be translated into 나는. Then after the word 나는, we will use this word as the input, and this input will be again trained into the RNN, and through the softmax we will create what is the possible next word. For example, the possible next word is 행복해. And this will be the input for the next states. After we have the next states, we go again to the RNN. And for example, you know, in English, we have the word I am happy. So the word always follow with a verb am. So when we do the translation to English, we need to have something. For example, ita, etta, ada, something that representing the verb. Okay. Sometimes, it happens that this might be very low in the probability. And if it is very low, then maybe we can omit it. Or if it is high, then we can use it. That's why whenever we do with the encoder, decoder, there might be some mistakes, or there might be some, we call it hallucination and other things, because they based on the probability. And if suppose there is a word ita, and then the word ita goes back to the network, and then let's say this is the end of the sentence. So the decoder starts with the context factor and initial input. This is the context, and then this is the initial input. And there will be a special token that indicates the start of sequence. So the start of sequence, this is the SOS. it predicts the word nanan here. Then use that word as input to predict the next word, which is hangbokin. And it continues this process until it generates the end of the sequence. Each step use both of the context factor and previous hidden states to generate the next one. So every this one, it will use the context and it use the hidden state. The first hidden state is H0, and then we have H1, and then we have H2, and then H3 until the end of the sentence. So adapting it remembers the prior sequence. So we expect that this network remember what was the previous sequence, and then it can predict what will be the best representation for the output. So the attention is something that can be extended into the encoder and decoder. When we apply the basic sequence to sequence, the previous one, we saw the encoder, decoder. So the model stops making prediction after outputting the end of sentence token. So after we have the EOS, it stops. But we want to have an attention. So what is attention? It is an enhancement to the basic sequence to sequence model. So the attention mechanism allows the model to focus. So this is the keyword, focus on different parts of the input sequence at each step of the output generation. So whenever we have the input, we will have the output, and now we are going to focus on the output. So the output can be more precisely to create a text, to create a sentence. This helps in handling longer sequences more effectively. So if the sentence is short, you can use the encoder, decoder. But if the sentence is long, then it is more effective to use attention. So the basic sequence to sequence, you can see something like this one using the encoder and decoder approach. If we have the sequence to sequence with attention, it means after we have the input and the output from the encoder, x1, x2, x3, xt. So after we have the context, then this will be applied for every of the step. There are many variations about the attention. The basic one is the encoder. Every output in the encoder, let's say I have the word hi, I am fine. So when we have this encoder, so we will generate an output. After we have this one, we will generate an output. After this one, we have generated an output. We have generated an output. We generate an output, and this output will focus on some of node or the hidden layer, and this will be the attention to create the decoder. After we have the output here, so it will be combined to be an input for the decoder, and so on. So the attention can be in single attention. In single attention means we have only one, or the attention can be multi-attention. This is more than one. There is a very important paper for the attention written by Vaswani et al. In 2017. This paper described the attention function as mapping a query. So there is a query here and a set of key value pairs. Key value, and key value. If you learn the Python, we have dictionary. In the Python data structure, the dictionary, we will have a key, this is k, comma v, this is value. The query means something that we want to look at, or this is something that we want to focus. If we have the focus on particular word, then we will calculate the number in the query according to the key and value. So that's why when we have this kind of attention value, it means this is the combination from the query combined with the key and value. The output is computed as a weighted sum of values. So weighted sum of value means we want to sum and there is a weighted weight on the particular input, where the weight assigned to its value is computed by a compatibility function of the query with the corresponding key. So it will be based on the corresponding key. So the query and the key value pairs are used in newly proposed attention mechanism that is used in transform. So the basic idea of this attention value, we will use it in the transform. We have the query, we calculate with the key and values, and we got the result with the attention value. And this attention value is the basic of the transform. These inputs for the attention mechanism are obtained through multiplication of the general input to the encoder or decoder with different weight matrix, as can be seen in the figure. So this is the figure. We have the query. Again, we have the key and value, key and value, key and value, and we get the attention values. So let's see with an example about the attention. Actually, when we do with the Q, K, and V, it should be a matrix. So Q, it can be a matrix, and the matrix, it depends on your embedding. So if your embedding is a matrix 5 multiplied by 1, then it means there will be like 5 column and we have 1 row. Or if the Q, the query, you want to query 2 words, then it can be like 5 multiplied by 2. So this kind of query can be different in many cases. So for the simplicity, let me just use a factor of 1. So how we can calculate the query and the key and the value. So suppose we have 3 words. Alice is fat. Why not put this comma? Maybe this is not. Yeah, you don't need the comma. Alice is kind. Okay, I want to have Alice, comma, is, comma, kind. Then let's say I want to focus on the word kind. So I want to focus on the word kind, and this is the query. And we want to evaluate how much attention it should give to each word. So let's say in the query Q, the factor, I just make simple with one factor of length 1. So this is a number. The number is generated using the embedding factor, whether you want to have the highest number or the lowest number. And the key or k factors. We have the word Alice, is, and kind. And this key is based on the dictionary, like the k when it is Alice, so the key is 1. The key for is 0.5, and the key for kind is 2. And we have the value which represent the meaning of each word. So the meaning, it means if I have the key is 1, then the value is 10. When I have the key is 0.5, then the value is 20. When I have the key is 2, then the value is 30. So something like this now. And we can try to calculate the attention score. The first step is to calculate the attention score, or we call it the query key similarity. So the query key similarity means we just do simple the multiplication. Q multiply by K. Actually, as I mentioned to you, I make it simple with the length of 1. So you can see the multiplication directly. 2 multiplied by 1. 2 multiplied by 0.5. 2 multiplied by 2. But actually, when you do with the neural network, it is a matrix. This is also another matrix. So the matrix can be something like this one. Let's say we have 5, and we have another matrix. Let's say we have 5 rows and maybe 3 columns. It depends on how many layers do you generate in the neural network, how many layers do you use the embedding, and etc. And it will be very different. So the simplification, just multiplication. You can do the multiplication of the matrix, but I have a single value. Then we have the numbers like 2, 1, and 4. After we calculate the attention score with the query key similarity, we can apply the softmax to get the attention weight. So the attention weight with the softmax function, you can apply with the E. Okay. e power of xi divided by the sigma of e power of xj for all j. So we want to sum of all j. For example, for the Alice, it is 2. How can we get 2? 2 is from the previous score. 1 is from the previous score, and 4 is from the previous score. Then we will do the e power of 2. E power of 2 is 7.39. For the word is, because the score is 1, so e power of 1. For the word kind, we have 4, so it is e power of 4. As a matter of fact, again, this number, because I simplify into 1, so we just have 1. But if it is a matrix, then you need to calculate each of this element of the matrix with the e. And then finally, we can do the softmax by looking at this formula. So for the Alice, the weight is 7.39 divided by the summation. What is the summation? The summation will be 7.39 plus 2.72 plus 54.60. So this is the summation. And we know the weight for Alice is 0.114. That is the 7.39 divided by 64.71. For the word is, this is the formula. For the word kind, this is the formula. So we have the weight. After we have the weight, then we can calculate the final attention. So the final attention means I would like to multiply the weights with the value. So what is the values? So we have the key, we have Q, P, and V. So we want to calculate with the value which is 10, 20, and 30. And we can get for the weight from the Alice, we will multiply with 10. The weight from the word is, we will multiply with 20. The weight for the word kind, we will multiply with 30. And at the end, we will have the final attention output, which is this number. So this is a simplification. As I mentioned, the dimension is 1, so the value is 1. But if it is a matrix, then the value will be in terms of matrix. So the final output of the attention mechanism for focusing on kind is 27.27. So this shows that the model mostly focuses on the word kind, which has the highest weight. So if you look at this one, 0.114, 0.042, and 0.843. So the highest weight is in the third word. This is kind. And after you multiply with the value, again, you can get also the final score, which is the highest, is the word kind. After the word kind, the next important word is, and the next important word is this. So by looking at the attention weight, and if we want to look at the word kind, for example. So kind, is there any similar of the word kind in our sentence? Okay, we can find kind. Then we put attention on this word. And then next we put attention on Alice. And next we put attention on this. This is based on the numbers. Let me stop here. Let's have a break. I will continue on.